It's a great, great pleasure to get to be part of this session. And my talk is called Consciousness as a State of Matter. Now, you were joking a bit yesterday about this book that I published yesterday. And if your jet lag is so bad that the book doesn't succeed in putting you to sleep, I also published yesterday on the archive a paper which will definitely do the job. I think it's the longest and most sleep guaranteeing paper ever, probably. I don't remember spending longer time working on any other paper in my life. So if this doesn't do it, I don't know what's going to put you to sleep. And
to define consciousness, we must first destroy it.
Yes, exactly. The book, of course, is about cosmology, about quantum information, and many other things. But the most controversial idea that I explore in the book is the idea that mathematics can describe not just some aspects of our world, but all of them, which would imply that it can also describe ultimately consciousness. And that means, so I want to look at what happens if we then say, let's try to think of consciousness as a state of matter. We think of other states of matter in physics, solids, liquids, plasmas, etc. And what we've discovered over the centuries is that when we take enormous numbers of particles and put them together, very new, interesting emergent phenomena happen, which can sometimes be quantified by a small set of things we can go out and measure, like the viscosity, the compressibility, etc. For instance, if some substance, which is kind of homogeneous, has an almost infinitely high viscosity, so it's very rigid, we call it a solid, otherwise we call it a fluid. If the fluid has a very low compressibility, we call it a liquid. Otherwise, if we call it a gas or a plasma, depending on the conductivity, etc., etc. Of course, there are very, very many different kinds of gases. But the beautiful thing in solid-state physics, and physics in general, is that it's still very interesting to look at the substrate-independent aspects of gases, which they all have in common. They all obey the Navier-Stokes equation. You know, they have different viscosity parameters in there, right? But there's a lot of cool general stuff we can do. So what things like that, in that spirit, can we physicists say about consciousness? There were a lot of questions and requests for Hamiltonians to Giulio and Christoph Koch. I promise you Hamiltonians. All right? So let's go beyond the gas, liquid, and solid here and look at some substances where there are interesting properties to do with information, the theme of our meeting. Let's look at, for example, at memory. Memory also has, any kind of good memory substance has a very large repertoire of long-lived stable states. You can also say that about my ring here, which has Maya's name engraved in it, and it still will in 1 year. But as opposed to, whereas if you engrave somebody's name on the ocean surface here, a liquid, it's not going to be there a second later. Memory, something we call a memory, also should have other properties, like it to be easily writable, more easily than engraving in a solid. Computronium is a popular buzzword in science fiction, the most general computational kind of matter. It shouldn't just be able to store information, but it should also have complex dynamics, right? Turbulence of a gas can also be very complex, but a gas is pretty useless as a computer, as Scott Aronson can certify. Consciousness needs to have probably this principle of integration, which Giulio Tononi and Christoph Koch highlighted so beautifully here. And what makes me so interested in this topic, and my big focus in this paper, is not to try to say interesting new things about neuroscience, where I have nothing on titans like Christoph Koch and Giulio Tononi, but rather to take these same ideas and say, what can they do for physics? Can we identify some set of principles which capture sort of the essence of all kinds of consciousness, and then use that to say something interesting about the physical world? Let me also, as a background, say why I'm so obsessed about this problem. Ever since I first met Bill Poirier in grad school 23 years ago, he's a little bit younger here, and he taught me information theory. I've been just haunted by this question, which I call the physics from scratch problem. Suppose you just give me the Hamiltonian and the density matrix. Let's go non-relativistic quantum mechanics for now to keep it simple, okay? Is it possible from just those two mathematical objects from just those two matrices or operators to figure out everything and to understand why we perceive ourselves as living in a three-dimensional space with this hierarchy of objects. After all, I look at you, I see all my friends here, but I also see a vast number of quarks and electrons. And if I only looked at these quarks and electrons, how could I just, by looking at that picture, figure out how these get perceived as grouped into objects, then which of these objects are conscious, and so on? And my vision with this all along was that, well, you just give me a Hamiltonian alone, what properties does it have? Well, you can pick any basis you want of Hilbert space, so the only property it has is its eigenvalue spectrum, its energy spectral density. What can you possibly do with just a bunch of numbers? Well, actually, a lot. A typical, breaking the world into subsystems in quantum mechanics corresponds to factorizing the Hilbert space, a quantum factorization problem, right? And a typical Hamiltonian cannot be factored. It doesn't have a tensor factorization, which is awesome. Which means if we look at the best factorization we can do to try to break it into two subsystems with the smallest possible interaction Hamiltonian, there is some unique best way of doing that. So my vision all along with this was do the math, which took me many, many years, and then find what the best factorization is of the standard model Hamiltonian, hope that space would pop out, the kind of factorization that's implicit when we write the Hamiltonian as an integral over different positions. And then the part that can't be factored, that's the interaction Hamiltonian, which gives us the forces telling us how all the different things interact with each other. I'll show you that I finally managed to do that, but that there is a very evil twist to the problem, and we need more to add to this. And I'm hoping the integration principle is exactly what we need in addition. So here are the 5 principles that I explore in this paper. A bunch of it is just straight Tononi and Koch here. The information principle that a conscious system has substantial information storage capacity. The dynamics principle that the conscious system isn't just storing information, but it's processing it in some interesting way. So that's where the Hamiltonian is going to come in. The independence principle that a conscious system has substantial independence from the rest of the world, so you feel like an autonomous system, roughly. The integration principle that a conscious system cannot consist of nearly independent parts. And the utility principle might be needed also at some point to say that we really perceive the things which are useful for us. I'm using a number of I've been trying out a slight set of variations of the integration principle here, not all of which are exactly like Giulio's. So any credit for the successes of this integration approach should go to Giulio Tononi, Christoph Koch, and their collaborators here like Larissa, and any blame should go to me for botching it and doing it a little bit wrong, right? I want to stress that the hope for me as a physicist is that even if we've only found some necessary conditions for consciousness that aren't sufficient, they can already be very useful to us. Because in the physics from scratch problem, right, if I just look at all of you quarks out there, right, and I want to know what does this world feel like to you, the thing I need to do is identify the different observer moments or consciousnesses in this here, and then ask how each one of them perceives this, right? And it's very interesting that Hugh Everett, all the radical and controversial work that he did on the Everett interpretation that he published in 1957, only needed one of these principles. He didn't need to know even about integration. He just said, suppose we simply assume that a necessary condition for consciousness is that it can store information. Then look at any information storage device, hard drive, whatever, okay? And he said, suppose it obeys the Schrödinger equation, what happens? And he got all this nice stuff and emergence of probabilities that we all love to argue about, right? So my hope is that by adding maybe one or some more principles, again, we can get a long way towards solving many of our pesky physics problems, even without having sufficient conditions for consciousness. So that's another thing which very much motivates this. Let's talk a little bit about integration. How many femtoseconds do I have left? 11 femtoseconds? All right, 10 to the 15. Good, good. So let's talk a bit more about integration first of all. What I very much tried to do in this paper is extend the beautiful work of Giulio Tononi and others, Giulio Tononi's framework here, to more general physical systems that aren't necessarily neural networks or even discrete. So I start with a Hamiltonian, a density matrix rho, and I go from there. And what's very nice about the whole information concept, and what made me so electrified when I first learned about all this, watching a talk by Christoph Koch and then reading Julio's paper, is it's full of mutual information and things which we know how to calculate in physics, not just for neural networks, but for anything. In fact, I learned about mutual information in quantum mechanics from you, Bill, 23 years ago, right? So look at this system, for example. This is I'm just showing you the Ising model here for various values of the parameters. You can slice this system into two parts and calculate the mutual information. And on the left side, you have no mutual information at all. It's just random. It's very high, the high temperature limit. But you have a lot of entropy. A lot of information can be stored in such a thing. On the other side, if you have a lot of correlation, then you don't have any entropy at all. You can't store any information. So if you want both the information principle and the integration principle to be important, you want to be somewhere in the middle. In fact, if you tune the Ising model to be very close to the critical point, or if you take your brain and you think of it as a solid state system near its critical point, you get very, very long-range correlations near this phase transition. Then you still have a significant amount of entropy. So there are many different states. You can have a lot of information. But it's also quite integrated now because you have these big contiguous blobs here, right? Which you can think of also as error correction in a way. If one of these neurons dies, you can reconstruct what it was from looking at its neighbors. And there are loads of connections with just classical information theory here. So just to remind you, for instance, if I take 8 bits and I put them in a bit string like this, there are, of course, 2 to the 8, 256 bit strings I could pick. But then I can't have any integration. Suppose I only pick square root of 256, 16-bit strings, the way Hamming did. Now I can only store 4 bits instead of 8 bits of information, but I have a lot of integration. If I lose 1 bit, I can figure out what it was. I can lose up to 3 bits, actually, without losing anything. Here I'm just plotting the integrated information defined as the mutual information when I chop off the cruelest choice of 3 bits. So I try all possible permutations here. My calculations were also very painfully slow because of the same the n factorials that you were up against here. Hamming isn't so great when you cut it exactly in half, even though you can always recover any 3 bits. But if you do random codes instead, you pick a random subset of 16 different bit strings, it's pretty nicely integrated pretty much for whatever cut you kind of do. Here I'm showing a more aggressive thing. I do 14 bits to 4096 possibilities. And you see that the best integration you get is if you're not too greedy and try to store all possible states. If you go by half, sort of the golden middle, then that's when you get the maximum amount of integrated information. And these random codes in classical information theory are very powerful. Here I'm just going more and more and more. And it seems that Scott probably would know better than I if there were any rigorous theorems, but that you can actually build a classical state where you have as much integrated information as you want. If you want a gigabyte of it, you probably need to have a system which can have about 2 gigabytes of information. You use about half of it for redundancy. So that's kind of encouraging. You can think of, in the language that Hopfield used when he came up with his Hopfield model, of having some complicated physical system with some Hamiltonian, some potential energy landscape like this. And if you have 256 potential wells that you could be in, this is a great memory device for storing 8 bits, right? But there will be no integration of this information, because if any one of the bits is lost, you could have been in any of the other states. The Hamming code corresponds to using only 16 of these. That's a little bit more like a typical Hopfield network, where most neuron configurations are not firing patterns, are not detractors. And but there are only a small number that you can sort of flow to, which can be stable states. And what's kind of beautiful about the Hopfield model and other simple neural networks is it very naturally gives you integration in the brain, just from the very nature of it. It sort of has built-in error correction that if you go a little bit off from this, you get sort of pulled back towards it. So that's also kind of encouraging. But this project has been the biggest roller coaster of any project I've ever worked on, because there were so many moments when I got super excited, like when I heard about your work, and then so many other times when I was very disappointed that something kept slipping away. When I solved some problem, it didn't work out as well as I hoped. The Hopfield network, for example, if you take 10 to the 11 neurons, you can only get 37 bits of integrated information. Oops. And that this doesn't quite feel enough to capture your I hope maybe there's something more, but maybe we're kind of Hopfield for the way we store memories, which is unconscious, and maybe the conscious parts of our brain is wired a little bit differently. Maybe we can get much more than 37 bits. Very cool problem in information, classical information. But another big disappointment I had was when I brought the Hamiltonian in and it went quantum information in qubits with this. So here it turns out that actually you can only do a quarter of a bit of integration if you just limit yourself to the state and don't bring in the Hamiltonian, which was going to help us a little bit, all right? So I want to cut to the chase, so I'll be super brief on this, but let's bring in first perfectly correlated classical state. 2 bits. Density matrix looks like this. 1 bit of mutual information. Awesome. Ta-dam, ta-dam. But this is quantum mechanics. We can now not just do a cut in Tanoni spirit by picking out one of the separating 2 bits, but we can do a unitary transformation first, which can turn this matrix into that matrix, which is a tensor product. So this point here, with 1 bit of mutual information, 0 bits of mutual information. That sucked. Okay, but we're quantum. Let's bring in the best artillery we have, the bell pair. Dum da dum. Bell pair has 2 bits of mutual information because we can reach this region with entanglement. Yes. Except it's a pure state, so we can do unitary transformation where it looks like this, which is a tensor product. 0 bits. The bell pair is not integrated at all on a different basis. And remember, we're talking about the whole world now. There is no outside. And there still are states, like this one, which have integration, no matter what unitary transformations you make. If you have a diagonal density matrix with probabilities 1/3, 1/3, 1/3, and 0, you can permute the eigenvalues whatever way you want. You still get something. This is your quarter bit. Sadly, it turns out, in the quantum integration paradox, as they call it, even beyond Hopfield networks, do whatever quantum system you want, as big as you want, never get more than a quarter of a bit. What does this tell me? It tells me that we can't just look at the density matrix at the state of the quantum system at one instant. The Hamiltonian obviously is important also. It's much harder when you're given the Hamiltonian and the density matrix to do some unitary transformation that trivializes them both. So that gives hope. And the last, I'm not going to give you any grand answers to these things. Let me just highlight a few more interesting things that turned up. So in quantum mechanics, of course, separating the world into pieces means we pick a factorization and write the Hamiltonian as some part which acts on the first system, plus a part on the second, plus an integration term, okay? The reason the paper is full of equations is because it turns out to be very useful to do a bunch of math on this, use the Hilbert-Schmidt vector space formalism and think about this all in complicated geometric ways, and was actually able to prove rigorously for a specific case and give good numerical evidence for the general case that when you do this thing and divide the world into pieces to get maximally independent, the best decomposition always happens in the energy eigenbasis. Okay? And that's pretty shocking, because that means that all your systems will always have Hamiltonians internally that commute with the interaction Hamiltonian. So there will be no quantum effects at all. And even worse, you actually get what I call this quantum Zeno paradox, which is even stronger than the quantum Zeno effect that says if you measure something very frequently, the change stops. Here, whatever you do, pretty quickly you end up perceiving just the world which is completely static, because decoherence pushes you towards eigenstates of these interaction Hamiltonians. Pretty soon, nothing happens. So this is obviously not the world we live in, which means yet again, we're missing some kind of principle. And dynamics seems very crucial here. And indeed there is, I want to just stress, built into the beautiful formalism that Giulio presented, there is already, in a sense, a Hamiltonian, because he has in his definition how the current state constrains the past and the future, right? And this makes a big difference. We would like to have some kind of complex dynamics, and I'm just going to cut to the conclusions. There are a lot of systems, which you can read about in the paper if you're interested, which have actually very high autonomy in that they're very independent, but they also have internal dynamics. By sort of sliding along the diagonal of the density matrix according to the internal Hamiltonian of the system, and then in such a way that the decoherence, the interaction with other systems, just keeps suppressing off-diagonal stuff and has almost no effect on you as long as you're pretty diagonal. The whole pointer basis of Zurich, the stuff that emerges from quantum Darwinism is very much of this type, and I'm just going to summarize by saying, I think it's just really, really fascinating what a breath to sort of work on further in strengthening the links between the problems we're struggling with here in physics and the problems that you guys have struggled with in neuroscience. I'm really convinced that they're very strongly linked, and that what you're doing can be very, very valuable, not just for deeper understanding in neuroscience about what consciousness is, but also very much in helping us with some of our peskiest problems. Thank you.